Hi friends, welcome to Curie Electronics. This is the fifth part of Technical Assistant Electronics 2019 VSSC question paper solution. We have completed up to 40 questions we have solved. Now today we'll solve another 10 questions. So let's start. Question number 41. A 100-watt power transistor having thermal resistance theta Jc, that is between the junction and the uh, case of 1.5 degree Celsius per watt, and maximum junction temperature specification of 150 degree Celsius is mounted on a heatsink giving theta Ca value of 1.0 degree Celsius watt per watt. If the combination is used in an automobile control system where the ambient temperature can reach 75 degrees Celsius, what is the maximum power that the transistor can dissipate? Now he has given theta Jc, that is between the junction and the case, that is 1.5 degrees Celsius per watt, and theta Ca 1 1 degree Celsius per watt, that is between the case and the ambient. Now what is P max power? The P max, the maximum power that can dissipate, the transistor can dissipate, is given by this equation. T junction temperature minus T ambient temperature divided by QJC plus QCA. Now we'll put the values. What is TJ? Junction temperature equal to 150 degrees Celsius minus ambient 75 degrees Celsius. QJC. What is the value of QJC? That is 1.5 QCA equal to 1. So we will get 75 divided by 2.5. We will multiply numerator and denominator by 10. That is 750 divided by 25. Now we will simplify, we will get 3. 30. 30 we will get. So the answer is option A, 30 watt. Question number 42. The capacitance per unit length and characteristics impedance of a lossless transmission line are C, and this is the capacitance per unit length. C is the capacitance per unit length, and this is the characteristics impedance of the transmission line. What is the velocity of traveling wave in the transmission line? The velocity of transmitting wave, or velocity of the traveling wave, is given by 1 divided by characteristic impedance multiplied by the capacitance. So the answer option B. Question number 43. What is the VSWR when feeding an RF signal to a 55 ohm load through a coaxial cable of characteristic impedance 50 ohm? So our load is equal to is CL equal to 55 ohm, and what is the other characteristic impedance equal to 50 ohm. Now VSWR equal to what? VSWR equal to mod of 1 plus rho as a reflection coefficient 1 minus reflection coefficient. You remember this thing, this reflection coefficient, this VSWR can vary from 1 to infinity, and is a reflection coefficient. Rho is the reflection coefficient. Reflection coefficient. And VSWR is the voltage standing wave ratio. Voltage VSWR. This can vary from, okay, that I already told you. Voltage standing wave ratio, that's a full form. Rho can vary from 0 to, the reflection coefficient can vary from 0 to 1. This you should remember. Now, to find VSWR, first we have to find the reflection coefficient. Rho equal to, rho is given as, I'll write it in a green color, ZL reflection coefficient. Uh, reflection coefficient. Okay, reflection coefficient is given by ZL minus Z naught divided by ZL plus Z naught. ZL plus Z naught. Now, so 55 minus 50 divided by, what is the load? Again 55 plus 50. So 5 divided by 105. 5 divided by 105, what it comes? When we solve, we will get 0.05. 0.05 will get it. Now reflection coefficient we know. Now we will put it in the VSWR. Okay. VSWR equals 1 plus mod of 1 plus 1 plus rho. What is the reflection coefficient we got? 0.5. 0.5 divided by 1 minus 0.5, that is, which equals 1.05 divided by 0.95. It comes to 1.1. So the answer is option D. When a wave travels through a transmission line, it will get reflected. So what percentage is reflected, that is given by the reflection coefficient. For a wave to pass through a transmission line without reflection, the load impedance and characteristic impedance has to be exactly equal. So we'll go to the next question. Question number 44. Question number 44. The K-map given below represents the bit G2 for a 4-bit binary. B4, B3, B2, B1 to gray, G4, G3, G2, G1 converter. What will be the expression for G2? The simple question is simple like this. What is the output of this Carnot map? That is the question. Now we have this is a chord. If we see this K map, this is a chord, and these two also we can make it a chord. So when you solve a chord or four ones in a Carnot map, we should get two variables as the answer. So first we will solve. See, once you simplify this chord 1, I'll take it. If we simplify this, what you will get? So here I'll write it on the left. This is B4 bar B3, and this is B4 B3, and on the top this is B2 bar B1 bar, and here it is B2 bar B1. Now if we combine, what happens? This B4 and B this will cancel, and here what will cancel? B2 bar B1 bar and B2 will cancel. So when this chord simplify, we are getting a output like this, that is B2 bar B3. B2 bar B3. We got it from first chord. And now we'll take the second chord. See these two. This combined is the second chord pair. That means a group of 4 ones. When you solve a group of 4 ones, here also I'll write it. Here what is there? B2 B1, and here what is there? B2 B1 bar. And this side I'll write it. What is this? Here the last two, no? So here is B B4, B4 bar, B3 bar, and this is B4, B3 bar. Okay. Now when you combine these four ones, what cancels here? The B1 and B1 bar will cancel. And what happens what in the horizontal direction? B3 bar remains, but B4 bar and B4 cancels. So we'll get a sum of products. That is, so what is the output here? What is left? B2 and B3 bar. So we can write it as output equal to y, output equal to y, which is equal to B2 bar B3 or what? Here, these two terms. What is left? What is left? That is B3 bar. B3 bar, B3 bar, B2. That is what left. Here, these two are B3 bar is left here. So now this is a exclusive OR gate. This output can be represented by B2 exclusive or B3. That is a XOR gate output. The output represents a XOR gate. XOR gate. Now we'll see the options. And the options, answer C is the answer. B3 exclusive or B2. So we'll go to the next question. Question number 45. A staircase switch. A staircase light is controlled by two switches. One at the top of the stairs and the other at the bottom of the stairs, such that the light is on when and only when one of the switches is on and the other switch is off. What will be the logic equation in SOP form, sum of products form? Sum of products form. So this is our stairs. Okay, now this is S1 and this is S2. Two switches are there. Now we'll write the logic for this. 4 states only we'll get. Normal our two bit combinations, that is 0 0 0 1 1 1 1 0. No, 1 0 1 1. Now what is the output? We'll take the output. At 0 0, staircase light is controlled by two switches, one at the top of the stairs and the other at the bottom of the stairs, such that the light is on when and only when one of the switches is on and other switches off. That means when both switches are off, the light is off. Let's assume this is our bulb. Light is off. When any one of the switches is on, light is on. Here also one of the switches are on. When both are on, light is off. That is 0. So this represents a XOR gate. This staircase switching represents a XOR gate. So already we saw what is the equation for XOR gate? A bar B or AB bar. So the answer is option C. We'll go to the question number 46. What can be the maximum clock frequency of a 10-bit ripple counter, which will cause a count to skip considering 10 nanosecond propagation delay for each of the edge triggered flip-flops? No. Clock frequency, FLK. Clock frequency is given by, what is the maximum clock frequency is given by 1 by n, number of flip-flops multiplied by the propagation delay. In this one, what is the propagation delay for each? See, this is a ripple counter. So this propagation delay get add a ripple counter. So what is the propagation number of flip-flops here? 10 flip-flops are there. 10-bit ripple counter. So 10 multiplied by what is the propagation delay given for each gate? That is 10 nanoseconds. 10 nano, very small, very fast. The time is very slow. We know only seconds. But electronics knows microseconds, nanosecond, picoseconds. Okay, now 1 divided by 10 multiplied by 10 to the power 10 nanosecond. 10 to the power 10 into 10 to the power minus 9. So which equals what? 1 divided by 10 to the power minus 7. This can be written as 10 to the power 7 hertz, or we can write it as 10 into 10 to the power 6, which equal to 10 megahertz. 10 megahertz. So the answer is option A, 10 megahertz. So this is because of it is a synchronous count. This is a ripple counter. If it is synchronous counter, what happens? Synchronous counter, there is no delay. F clock equal to what? 1 divided by propagation delay of the single flip-flop. Okay, you can solve it. 1 divided by 10 nanoseconds. It comes. Now you can solve it and find out what is the value. We would say synchronous counter. Question number 47. Calculate the fan out of a TTL circuit with the following specifications. IOL max 32 milliamps, IIL max 1.6 milliamps, IOH max 400 microamps, IIH max 10 microamps. This fan out, how many a single gate, fan out means how many gates one single gate can drive. IOL means maximum current. This fan out is given by FO. Fan out is given by the equation IOH, output at high state divided by output current at high state supplied by a single gate, and that are taken by each gate, that is IIH. If you use that equation, 400 microamps. One second, something is going wrong. Equal to this equation is equal to what? IOL, low state current, low output current, IIL. This is the equation to find out. The fan out. Now, what is our IOL? IOL max equal to? See here, here what happens? IOL max. So we'll use IOL divided by IIL. I'll try to make a video on fan out. It's a simple concept but useful. This is 32 milliamps divided by 1.6 milliamps. So we'll multiply by 10. 320 divided by 16. So that is 20. We will get a fan out of 20. So the answer is option B. See this. IOL, the maximum current we will get when it is happening current sinking, current sinking, current sinking, current sinking. Okay, we'll go to the next question. Question number 48. In the given op-amp circuit, find the current I0. I0 we have to find. So what I will do, here I will use a nodal equation at the output. I will mention here V out. This point I will take it as V out. And I'll assume that all currents are flowing out. The remaining two currents are flowing out. So now I'll write at this point, what is the voltage at this point? This is at 0 volt because of the virtual, virtual ground concept. Now, V out minus 100 minus 0 divided by 100 plus V out minus 0 divided by 25k. It's a nodal equations. All of you should know the nodal equation how to solve. I think I have one video on it. Please check and watch it if you don't know. Equal to 0. So this is V naught by 100 plus V naught by 25 equal to minus I naught. I'll write it as minus I naught. Now I'll multiply the complete equation by 25 to remove this. Okay, so it will become V naught divided by 4 plus V naught equals to minus 25 I naught. I naught. So what is the equation for I naught? What is the equation for I naught? I naught so first we'll apply LCM here. That is 4 V naught plus 4 V naught equal to minus 25 I naught. Minus 25 I naught. 5 V naught divided by 4 equals to minus 25 I naught, which equal to 5 V naught equal to 100 minus 100 I naught. I naught. Now we have to find out I naught. For I naught, we have to find V naught. What is V naught? Now we'll try to find V naught. We have to find V naught equal to question. Then we can get the I naught, the current we can get. So this is a inverting amplifier. It's an inverting amplifier. So V out equal to minus RF by RI multiplied by V in. V in. What is the value? Minus RF. What is the value of minus RF? 100k, 100 divided by, what is RI? 10 minus multiplied by V in equal to 1. So we will get minus 10. Minus 10 volt is the V out. Now we'll find I out easily. Okay. Instead of V naught, what we have? 5 V naught equals minus 100 I naught. Now in place of V naught, I will put minus 10. 5 minus 5 multiplied by minus 10 equals minus 100 I naught. So 1010 cancels. 10 I naught equal to 5. So I naught equal to 0.5. 5 divided by 10.5. So the answer is option B. Question number 49. Question number 49. An amplifier operating from single plus 15 volt supply provides a 6 volt peak sine wave signal to a 1 kilo ohm load. DC current drawn from the supply is 8 milliamps. What is the power dissipation in the amplifier? Power dissipation is given by input power minus output power, input power minus output power. This will give the power dissipation. What is the input power? Input power, what is the supply voltage? 15 volt. V into I. 15 multiplied by, what is the value of I? 8 milliamps. 8 milliamps minus, what is the output power? Output power is, what is the, say, output 6 volt, 6 volt peak. 6 volts peak. Power here, output power, we will use the power out equal to V square by R equation we can use. But given is the peak voltage, but we need it in RMS. So 6 divided by root 2 will give the RMS value of the output signal, divided by square, divided by, what is the 1 kilo ohms? 1. See, when we have three variables, voltage, current, and resistance, we need not write this milliamps everything. I told in many videos how to use it. So please follow it. That is voltage in volts, current in milliamps, and resistance in kilo ohms. So you have to keep it in same format. Then no need of for your calculation, these unit conversions. So 15 into 8. So 15 8s are 15 multiplied by 8. What you will get? 5 8s are 40. For 12, 120 you will get 120 minus 36 by 36. 6 square 36 divided by 2. That is 18. So what is the answer? 102 milliwatt. So the answer is option C, 102 milliwatt. When you calculate the output power, you have to make sure that you will do it in RMS voltage. You will take RMS voltage. So how do you feel? How these questions? So this is VSSC question paper. So you have to be a little higher than the diploma. Then only little more you have to be ready to face little higher problems than diploma. Then only you can get through it. This is today's last question. The reduction in gain of an RC coupled amplifier at high frequency is caused by. At high frequency, the reduction and the gain comes down. That is due to the internal capacitance of transistors. Option B. So friends, I hope this video is useful to all of you. Please share the video with your friends and subscribe the channel. I'll be solving almost all the question papers available for technical assistant, technician, electronics and electrical, and refrigeration related question papers. So thanks for watching. See you soon. Thank you.